Okay, so we were finding the magnetic field of the infinitely long current-carrying wire, and we ended up constructing the integral expression, and this is actually an integral in dy, so it looks like that, and we can use the following. But we notice that we actually have something here that's not equal to 1, so we have to change the variable of integration and pull out an x squared, and therefore it'll be a y over x squared quantity that we're integrating over. And so we'll end up with, let's just pull out the minus k hat, mu naught, I naught is the current, we have 4 pi. We will end up at something that looks like this, so I'm going to skip over a few calculus. Actually, these are just simple algebraic expressions. Let's see. From this is from y goes to minus infinity to plus infinity. And so we get that b ends up being, let's see, mu naught I naught times the value. Well, let's put the minus and plus infinity in afterwards. Let's just leave it in terms of some. Let's get rid of the minus sign here. Let's just call it a y1 and a y2, and then we'll plug in minus and plus infinity. So this is y2 over 4 pi x times x squared plus y2 squared minus mu naught. We could have pulled out the mu naught times I naught, but we'll just leave it in there. 4 pi x times the square root of x squared plus y1 squared, and there's a y1 here, and then of course we have the minus k hat still there. And so now we take y1 goes to minus infinity, and y2 goes to plus infinity. And so we see that this becomes infinity, and we have the square root of infinity squared, and this is irrelevant because it's a finite quantity, so we just get infinity over infinity. And so we end up with b equals mu naught I naught over 4 pi x times infinity over infinity, or let's just keep it as y2 over y2. Those are the only terms that matter. We have minus, but we have negative infinity. So here we have minus, let's leave it as y1, minus y1. Well, yeah, that looks a little weird. But we'll end up with, all right, if I think of, well, I wrote y1 equals minus infinity, so let's just we end up with a plus 1 here, and that's really a 1 as well. So, and, sorry, forgetting my terms here. I still have the unit vector minus k hat, and so overall I'll get mu naught I naught. This becomes 2, and I have a 4 here, so I get a factor of 2 pi x, and I get the minus k hat. That's my final expression, but I used the coordinates, so here was my infinitely long line, and this distance here, I call that x, but maybe more generally we can just call it r. and the field there is pointing into the page, but more generally we can say that the magnetic field is mu naught I naught over 2 pi r times phi hat, because the field circles around. So if we look at it sort of like that, where the infinitely long line is coming right at us, then we would see a field that's circling around. So here is the current, the infinitely long current carrying wire, and the field is circling around that wire. And so, by the way, the Biot-Savart law has this expression mu naught I over 4 pi integral I dr cross r hat over r squared, and this part is useful in figuring out the direction of the magnetic field. So dr is the direction of the current, which is out of the page, and so it's my index finger and the middle finger. Let's say I want to know the field here. I point my finger up the page and my middle finger to that point, and I get that the field is pointing that way. Right? So the field here is pointing that way, and it's circling around. So this is the direction of the magnetic field, and that's why I use a phi hat, indicating that it's sort of circling around in that way, and it's decreasing as I'm going further out, so my arrows will become smaller, but the geometry is the same. The field circles around. So the magnetic field has this property that it, unlike the electric field, it doesn't diverge radially away from the source of the magnetic field. It circles around the source, and therefore in finding the magnetic field is more complicated, and it won't be a Gauss's law for magnetic fields that's useful for us when we're trying to take advantage of symmetry properties. So that's the direction we're heading in.